Okay. Perfect. All right. All right. 9:45. Packed house. Let's get started. All right, Lord, thank you for bringing us together this morning. Thank you for everything that you do for us. I pray that you keep us focused, that you help us to just finish the race of this semester. In your name we pray. Amen. All right, so let's see, does this one work today? Maybe, maybe not. Who knows? All right, so we're going to recap, and then we're going to talk about transfer functions and impedance. And then we're going to do a bunch of problems. Like the rest of the week, we're just going to do problems. Okay? So that's what we're going to do. All right, so maybe nobody ever filled this out at the end of last class. I don't know. But I'm going to take this to mean that everybody understood everything completely and there's no problems. Oh, I'm being corrected. Melanie, yes, question. All right, give me 1 sec. I'm going to do that. So it was asked if we could go over question 6C from the homework, since it is a cosine and sine inverse Laplace transform. And we certainly can. Give me 1 second to add a slide here, and then we'll go after it. Oh, wrong. Helps if you use the right keyboard. Right, let me add a slide here. Okay. So Melanie asked if we could go over problem 6C from homework 5. Right. So why don't we check it out? Just pulling up my homework 5. It's cool, guys. It's cool. It is. So problem 6C gives us the Laplace domain variable y of s is equal to 2s plus 18 over s squared plus 8s plus 20. Okay. First step that we always want to do as soon as we get one of these, right, is check the roots, right? We always want to check the roots. So 6C. Right, so if we check the roots, what do we get? What are the roots of the denominator? What are the roots of the denominator?
Is it -4 plus or minus 3j or 3i?
I don't know why I put a hat on that. There's no hat. It's just regular j. It's not a unit vector. right? So yeah, so what kind of roots we have, right? We've got a complex conjugate root set. Right? We've got a complex conjugate root set. Because we have complex conjugate roots, we automatically know that we should be getting a damped sinusoid out of this, right? That is something that we automatically know. If we don't automatically know that, please review the lecture from a few weeks ago where we went extensively through root responses, or come to office hours, right? And we can talk about it, okay? So what do? Well, we don't want to factor this, right? Because the J in the denominator doesn't help us. So how do we handle this? Well, we know that there has to be two roots. So we can do our partial fraction expansion using this formulation, right? Where A and B represent the two root responses, right? And I know from the Laplace transform table that this means that I need, well, before we get into that, right? I can simplify this still, right? Because what form does this need to take? Right? What form does this need to take? This needs to be in the form, right? Remember that cosine of omega t times e to the negative at has a Laplace transform of s plus a over s plus a squared plus omega squared. Right? If I'm remembering that correctly, Dr. D should have pulled the Laplace transform table for this, but that should be for cosine e to the at, negative at. Right? And we also know that sine omega t, e to the negative at, has a Laplace transform of omega over s plus a squared plus omega squared. Right? So those are things that we know. So we need our denominator to kind of be in this form, right? And how do we do that? Well, we're going to have to use completing the square, right? So how do we do completing the square? Well, we take half of the 8, right? So 4, and then we square it, so we'll get 16, right? So we'll get s squared plus 8, s plus 16 plus 4, right? I mean, it's just separating this into the form that we know it has to take. And this now has the added benefit of us having something that looks like this, right? Where 2 is omega and A is 4. Right? So, right? So we end up with something like this, which is great. And now we're ready to do our partial fraction expansion. Now we're ready. Okay. Now we're ready. All right. Is everybody okay so far with this, right? Again, we know the root, so we know the form that the solution has to take. This is not cheating. This is using our knowledge to develop our solution, right? You know what it's supposed to look like. Make it look like what it's supposed to look like. Right? Remember, the Laplace transform table has to be exact in order for us to match, in order to use an inverse Laplace transform. So knowing this, right, we're pretty good. So basically, if you ever come across something with complex conjugate roots, you are 99% going to have to complete the square, right? to get it into the right format if you have a second order denominator. Okay. So this is where we're at. We got 2s plus 18, right? So let's write this down, right? So we know that from this, right, y of s is equal to 2s plus 18 over s plus 4 squared plus 2 squared, right? And I'm writing that as 2 squared instead of 4 to remind myself that 2 is omega, right? 2 is omega, a is equal to 4, right? So omega is equal to 2. That would be probably in radians per second. And a is going to be equal to 4. So this whole thing, right? Well, I know that this is going to be a sinusoidally damped response, but I don't know how much of it is going to be due to sine and how much of it is going to be due to cosine. And because we have two roots, we're going to have to solve for two constants. Okay. So we're going to split this. We're going to say that we have the sinusoidal portion, right, which is going to be a times 2 over s plus 4 squared plus 2 squared. And we're going to add to that the cosine portion, right? b times s plus 4 over s plus 4 squared plus 2 squared. All right. Remember, right? Remember. So where did you pull those from, Dr. D? Right? Where did you pull those from? Now remember on the previous page, I wrote down what sine omega t times e to the negative at was in the Laplace transform. That's a, right? This first part. This is sine omega t e to the negative at. And this second part is due to cosine omega t e to the negative at. That's where they came from. Those are just the Laplace transforms from the table that I've plugged in my values for, right? But I know that some portion of that has to be due to the sine, right? And there's some scaling factor A on there that's going to tell me how much of it is sine. And there's some scaling factor B there that's going to tell me how I'm amplifying or attenuating my cosine. Okay. So when we go for this, right, we're going to multiply through by this denominator, right? The s plus 4 squared plus 2 squared. Right, we multiply through on both sides, right? So I'll take this term, I'll multiply by s plus 4 squared plus 2 squared. I'll take this term and I'll multiply by this, right? And the nice thing about it is because they all have the same denominator, all the denominators cancel, right? And I did the same thing to both sides of the equation, so I haven't violated any algebraic rules or anything. So I'm left with 2s plus 18 is equal to 2a plus b s plus 4b, right? I just multiplied through b times s plus 4, just brought the b through it. And the reason that you want to do that is because now you can group my s to the 1 term, right? So s to the 1 is going to tell me what? 2 is equal to b, right? S only has 2s and bs, right? So hey, look at that. B is equal to 2, right? It's already done. Got it. And we've got s to the 0. Well, I've got 18 is equal to 2 times a plus 4 times b. I can solve this because I know that b is equal to 2. So a should be equal to 5, right? 4 times 2 is 8. 18 minus 8 is 10. 10 divided by 2 is 5. So now I have a and b. So what do I do with those? Oh, I plug them back in the equation up there, right? Let's see. Did I give myself another slide? No. Oh, give me a sec. I'm going to grab one more slide for this. Okay. Is everybody good so far? Tracking, yeah? Everybody at home doing all right?
Yes, sir.
Cool, cool. So, right, so now we're just going to take this, right? We're going to say, well, one more. There we go. Well, I can say, right, that y of s was equal to a times, well, just so we remember, right, is a times 2 over s plus 4 squared plus 2 squared. And b times s plus 4 over s plus 4 squared plus 2 squared, right? This is the equation we had on the last page. I'm just going to plug in a and b, right? So this is 5 times 2 over s plus 4. Let's write it so people can actually read it, maybe. Squared plus 2 squared plus 2 times s plus 4 over s plus 4 squared plus 2 squared. Then I'm using my inverse Laplace transform, right? So I take that into the table. I already know that that first one is a sine, right? Because remember, we already looked at that. And we said, well, we know that omega is 2 and a is equal to 4, right? That's a plus. So now when we take the Laplace transform, the inverse Laplace transform of y of s is y of t. Inverse Laplace transform of the first part here is going to be 5 times sine 2t, whole thing, times e to the negative 4t, plus 2 times cosine 2t, e to the negative 4. Right, or if you wanted to be a fancy pants, right? You could pull out your e to the minus 4, which is super fancy, right? Super fancy.
Dr. D,
Yeah.
can you show how you got 5 and 2 for A and B?
I can if PowerPoint will let me switch slides. Please hold. Microsoft's having an issue. All right. So, Dante, what you do, right, is you isolate the coefficients for s, right? I have s to the 1 and I have s to the 0, right? S to the 0 just being anything that doesn't have an s, right? Because s to the 0 would be 1. So everything that has s, I've got 2s is equal to bs, or 2 is equal to b. And everything that doesn't have an s in front of it, I've got 18 is equal to 2a plus 4b, right? So right off the bat, I'm already told, just from writing my equation out, what b is. Then I plug this in over here, right? And I can solve directly for a, right? Because 4 times 2 is 8, 18 minus 8 is 10, 10 divided by 2 is 5, a is equal to 5.
Thank you.
Mm-hmm. Any other questions on this one?
Yeah, Dr. D, I have a question.
Yep. So,
How do you know that there's a sine component and a cosine component just from looking at the original function?
Because when you have complex conjugate roots, you're always going to have some sine and some cosine, right? So we're going to talk about it more in frequency response, but the reason for it is because when you get a sine wave out, if you had a sine wave to start with, you're going to have a change in amplitude and a phase shift, right?
Okay.
And the cosine is the phase shift of the sine, right? It's just shifted by 90 degrees. So you're just, essentially, you've got this waveform that's going to be sinusoidal. I think the way that they show it in the textbook, right, the form that you normally see for this sort of thing, and this is a side note, right, is that your solution would take the form sine omega t plus phi, right? So some amplitude times sine omega t plus phi. Well, you could convert this into your phase angle, right? You could convert that into phase angle.
Okay.
It comes about, AJ, think of it in another way too, right? You know that it's going to be a sine wave, but you don't know directly just by looking at that transfer function or the roots whether it's actually a sine wave or a cosine, right? It might turn out that your cosine component goes away, right, and it's a pure sine wave, right? But because we started with something in this form, right, up here, right? Because we started with that numerator, if we go back and look at it, right, this has elements of both the numerator here and the numerator here, right?
Mm-hmm.
And so it has to be some combination of the two.
Okay. Thank you.
Sure.
Dr. D?
Yes.
Sorry, back to the question I just asked. So I just want to make sure. So you're solving for the ones that have S, and then the next step you do is without S, right?
So Dante, whenever you look at this here, you get this equation, right? Whenever you get this, whatever it looks like, right? You've multiplied through by your denominator, and you're just left with this right here, right?
Right. And what I did with that is I did 2S equals 4B because I thought I was solving for B, and then I would plug that B into the
Right,
A.
but that 4b doesn't have an s in it.
Right. Okay.
So group them by
Okay. Yeah.
the s variables, right? You're going to group all of your s squareds, right? So in some of them, right, you're going to group all your s's, right? Get the coefficients of all of these things from the left-hand side and equate them to what's on the right-hand side. So, right, depending on what order system you have, you're going to have that many equations and that many unknowns.
Yeah. Thank you.
What you're doing is you're trying to solve for A and B, right? This is the same thing as solving for your constants when you're integrating, right? This is like your C1 and your C2. This is what you're trying to solve for.
Thank you.
Mm-hmm. Mm-hmm. Cool. Anything else? Okay. All right, so let's name 5 things that we've learned in the past 10 weeks. Then. Anything, any 5 things. That's like, you only have to name like half a thing per week, guys. It's great. It's a great deal. So what's 5 things that we learned in the past 10 weeks? Kirchhoff, okay. I heard Kirchhoff. I'll take it. You know, I'll just write Kirchhoff laws. All right.
Order systems.
One more time, sorry.
Ordered systems.
Okay. Write my handwriting better. All right. What else? Yeah, no. Sure.
Rotational systems.
Okay. One more. All right. Josh, you got randomly selected.
Dr. D's 5-step method to solving problems.
All right. The Dr. D #1 super terrific. I forget the whole name. Problem solving method. Sure. Forgot my own problem solving method.
For free body diagrams, isn't that?
Free body diagrams. I'll take 6 FBDs. All right. So we've done quite a few things, right? Okay. Good. People were paying attention. It's always good. All right. So here's the topics for exam 2. In case you were wondering, right? You didn't know. We've got state space transfer functions and linearization from our modeling category. From the time domain response, first order systems, right? So we want to know, how do we characterize a first order response? How do we draw the response for a first order system by hand? Second order systems, what are the different root responses and what do they mean? What do we need to characterize a second order system? How would we go about drawing a second order system response? And if you're given the plot of a system response, could you generate the mathematical model? Right. And then Laplace transforms, right? Initial value, final value theorems, the different properties, but you guys have those on the master sheet, right? You got initial value theorem, final value theorem, and the properties, the important properties that you need on there. Inverse Laplace transforms, right? So we want to know how to do partial fractions just like we did previously, right? In the problem we just ran through, but also some of the other problems that we'll do today, right? We want to determine the system response using the Laplace transform method. We want to do the same thing using the transfer function method, and we want to know how to use impedance. Yeah, no. So the question was, after you do the problem all the way through, like, would there be a question that says, give me the game plan for how to model something and simulate? And no, that's not going to be added to the problems, right? Yeah, so don't. MATLAB and Simulink are nice tools and they're very useful, but we're not going to use them on the exam. Okay. We're not going to use them on the exam. Is calculator, master sheet. That's all you need. So we're going to cover a couple of these things today, right? So let's just refresh a little bit with these last 3 here, right? Because we did go over these a little bit, and we went over 2 of them last class, but we'll go over what these mean, right? So when you're asked to determine the system response using the Laplace transform method, this means you need to take into account the initial conditions, right? So you have your model, you have your differential equation, you take a Laplace transform of both the outputs and the inputs, and then you solve it for your output variable. Then you run through your partial fraction expansion, and that's that, right? Then you match it up with the Laplace transform table, and get your things out. Invert it, inverse Laplace. So how is the transfer function method different? Well, the transfer function method is very similar, except that we start by finding the transfer function. And remember, the transfer function tells you that we are supposed to assume 0 initial conditions, right? So even if you're given initial conditions, and you're told to use the transfer function method, don't do them, right? Use zero. If you don't use zero, it's not the transfer function, okay? So we find the transfer function, we do it all generically, right? We don't Laplace our input yet. We find the ratio of output to input, get our transfer function. Then we multiply our transfer function by the Laplace transform of our specific input. Then we do our partial fractions. Okay? Those are the two different methods. We can talk about impedance. Right? We'll talk about that today. The problems that we do, you'll see. We're gonna test a lot of these things. But let's watch a video on Laplace transform.
What is the Laplace transform and why do you need to study it? The Laplace transform transforms a function f of t in the time domain to another function, capital F of s, in the frequency domain. In the frequency domain, certain calculations become easier. So we transform our problem from time domain to frequency domain. We solve it, and then we transform back to the time domain. An excellent example for this is solving ordinary differential equations. You have looked at solving linear second-order differential equations of this type in the past. For homogeneous, meaning right-hand side equal to 0, second-order linear differential equation, the amount of work needed to solve when you do this in the frequency domain is the following. We take the Laplace transform of the whole equation, which is this. We know what the Laplace transform of 0 is, that's just 0. We know what the Laplace transform of this is, and also the Laplace transform of the second derivative, which comes to an equation like this, which we then simply solve for x of s, doing some rearranging of the equation. And we then transform back into the time space. And there is our solution to this initial value problem with a second order differential equation. Now that was an easy example because we were looking at a homogeneous differential equation. What if it is not a homogeneous differential equation? Take a look at this example. It is still a second order differential equation. It is linear, but on the right hand side we don't have 0. So if you were to solve this using the method you've learned before, you would find a general solution and you would find a particular solution and you would combine them to the solution. Now with the Laplace transform, we don't need to worry about any of this. Same as before, we simply take the Laplace transform of the whole equation. We know what all these Laplace transforms here are. We rearrange, and in the end, we've got our solution. Straightforward, without having to worry about particular solutions and general solutions. So this is much, much simpler. So what do you need to do to transform a function, little f of t, from the time domain to a function capital F of s in the frequency domain? Well, f, little f of t, and capital F of s are related as follows. Capital F of s is the integral from 0 to infinity of e to the negative st times our function little f of t dt. And this is also then written like that, Laplace transform of little f of t. Solve the integral and you have capital F of s. Often we don't need to actually solve any integrals as we have tables to read off the Laplace transform of a function. Here is an example of a table that we could use. For example, the Laplace transform of t squared would simply be 2 over s cubed without us having to calculate it every time we're looking for the Laplace transform of t squared. Now, transforming back from the frequency domain to the time domain, we also usually look up functions in the table. We just go the opposite way. So, for example, if we have the function 1 over s in the frequency domain, we know that this must be 1 in the time domain. So this was a very brief overview of Laplace transforms.
Beautiful. right, so that's Laplace transforms, right? Why are they useful? Yeah, Sean. It is not, but it will be included for you with the next exam. Of course, right? So next exam, we can talk about that. Talk about it next class. And we'll go through the whole rundown. But things you'll be given are the Laplace transform table, the master sheet, right? So we'll talk about how to do all that stuff at the beginning of next class, just so fresh for everybody, right? All right, so the nice thing about Laplace transforms, right, is that now instead of solving differential equations where we have to find a particular and a homogeneous solution, we take the Laplace transform of our equation, we use algebraic manipulation to solve it, and then we use the inverse Laplace transform to pull it back out, right? And that's what we're doing. So how does that relate to some of the other things that we can do, right? So the transfer function can be found for any model in the same way that we found it for mechanical systems, right? Which is invoking the dark arts, right? And all of that, right? So we can model a circuit, right, in this way too, because it's just an ODE, right? So you might have noticed that most of the systems that we've been doing so far for all of the Laplace transforms have been mechanical in nature, right? But there's a very specific methodology that we can use when we do circuit, right? So first, right, we create our model. That's the 5 steps that we always use. Then we take the Laplace transform, and then we find the ratio of the output to the input, right? We're just finding our transfer function. That's what we're doing, right? So let's do one together, right? So here's a circuit, right? Consider the RLC circuit treated in example 6.2.14, not from our textbook, and shown in this, right? Use the Laplace transform to obtain the differential equation model. And so we're going to use the Laplace transform to get our differential equation. Okay, so start with our diagram, right? Well, in the interest of saving space, and Dr. D will just do it the way that he wants you guys to do it, right? So we redraw our circuit. I've got some currents coming through here. I've got a node up here, right? We'll call this E1. We'll call this one E2. I've got current coming through here that I will call I sub L. And I've got some current branching here that I'm going to call I sub C. Ooh, actually, Dr. G drew that the wrong way, right? It's going to be this way. It's going to be that way. Which means I've got a KVL here, like this. Call this KVL right-hand side. And I'll have another KVL coming this way, left-hand side. Do my inputs up here. Input, E1, E2. Right, so I've got multiple inputs. Outputs. Well, remember, for electrical circuits, I want you to use IL and EC. Does it matter overall? No, it doesn't matter overall. No, you can use it. You can do this using EL and IC if you want. It's just that that's not the method that we've been doing, right? Just use the method that we've been doing. So that's my inputs, my outputs, and my diagram, right? Pretty straightforward. And make sure that you're drawing an annotated diagram with all of the things that you need to solve the problem, right? And make sure that you're doing it. So I've got that, right? I can write my truths. And this is just an electrical system. So we'll have, the standard Ohm's law. Right? We can't just call that IL or IC, right? Because it goes into a junction, it goes into a node, which is going to split it. So we have to use our KCL there as well. All right, so for our elements, we've got something that looks like this. We've got KCL at A, right, at that node A, which is going to tell me that IR is equal to IL plus IC, right, because I have IR coming in, I have IL and IC leaving. KVL on the right tells me that E2 minus EC minus EL is equal to 0. And KVL on the left tells me E1 minus ER minus EL is equal to 0. Those are all of the truths that I have and that I need. And so let's work our reduction. All right, we'll reduce this. So you can start with, KCL, KVL right, or KVL left, whatever you want to, right? I'm going to start with the KVL on the left-hand side. And I'm going to say, well, that tells me that E1 has to be equal to R, I sub R, plus L, I dot L. Right? So just taking the KVL, right? So this is from KVL left-hand side. Right? KVL out. Okay. All right. So now I'm going to take this KCL at A and I'm going to substitute in for IR. Right, so I'm going to take this right here and I'm going to plug it in down here, right? That's what I'm going to do. Take that equation and plop it in there. So I've got E1, which is allowed, right? Because E1 is my input, but I need everything in terms of E sub L and I sub L and EC, right? That's what I need. So this is going to be R times IL plus IC plus L I dot L. I can also plug in for IC, right? Because I've got IC in terms of EC, right? Which is what I want. So I can plug that in there as well. That's what we'll do. This is going to be R times I sub L plus C E dot C plus L I dot L. That whole thing's equal to E1, right? So this is an equation. And normally that'd be fine, right? We would just leave it there. And we're gonna leave this, we're gonna expand this right. We're gonna expand this slightly. And we're gonna keep all of our ILs on one side and move everything to the other side. And so L, I dot L plus R, I sub L is equal to E1 minus RC E dot C, right? So all I did was multiply through by my R and keep my ILs on one side and my EC and E1 on the other. We'll call that one equation 1, right? And we're going to need two equations because we have two energy storage. I've got my inductor and I've got my capacitor, and those things are storing energy. So I need at least one for each of those, right? So I need two total equations. Okay. So far, so good. Everybody doing okay? Any questions? Any questions? Nothing really crazy. Pretty straightforward. we need another equation. So where's that going to come from, right? Well, we still got a KVL that we haven't used, right? So we're going to take that KVL from the right-hand side. I'm going to write it in terms. I'm just rearranging this, right? This is from KVL on the right-hand side. Well, that's really nice, right? That's really nice. Because I can leave EC as is, and E sub L is just this. So look at that. I've got two equations. And normally we would just leave this, right, and we would just be done. But we were asked to find the original differential, like the big old differential equation, right? So you could take this and you could solve one of these for I sub L and plug it into the other, right? And do a bunch of crazy stuff. Or you could set it equal to E sub C, and you can solve this two different ways, right? It wasn't specified. We want it in terms of the voltage across the capacitor or the current through the inductor. It doesn't say. You can do it either way. But I think the one thing that you'll agree with me on is if you leave it in this form, then it's going to get a little bit gross, right? Because you're going to have to take an integral to get I dot L in terms of IL, or some other such method for doing it for E sub C, right? But if we take the Laplace transforms of both of those equations and then do the algebra and then pull them back out, then we've got something we can do a little bit more easily. So that's what we're going to do. We're going to take this first equation, right? I'll rewrite it on this page. Oh, I guess I won't because there's no other page. Please hold. Totally underestimating all of the slides that I would be needing today. Anytime, PowerPoint, appreciate it. So let's rewrite these equations, right? So I've got L, I dot L, plus R, I sub L, is equal to E1 plus C E dot C, which we called equation 1. And I've got E2 is equal to EC plus L I dot L, which we're calling equation 2. We're not given any initial conditions. Or what? So we can't use the Laplace transform method to do this, right? But we can find the transfer function, right? And for this particular system, we would have two possible transfer, or actually 4 possible transfer functions, right? Because there's one for each input-output pair, right? So you've got IL to E1, IL to E2, EC to E1, EC to E2. We're going to focus on the IL to E1 and E2 right now. Okay? That's what we're going to focus on. All right, so we've got to take a Laplace transform. Let's start with equation 1. All right, so I'm going to take the Laplace transform of equation 1. And if I do that, and we're using 0 initial conditions because we weren't given any, well, what do we end up with, right? We get LS plus R times IL of S.
Dr. D, do you mind switching the slide for us?
Sorry, forgot to unfreeze that. My bad. That should be better. Thanks, Pat.
Thank you.
So let's slow this down. Let's do this, all right? So I'm going to take the Laplace transform of the first. All right, so this is going to be LS IL of S plus R IL of S is equal to capital E of 1 of S plus CS EC of S, right? That's what we've got. And I can do some algebra, right? And I will. So I'm going to get LS plus R times IL of S, right? So I'm just grouping my like terms, just making it look nice, cleaning it up a little bit. I'm going to leave that for right now. I'll call this equation Laplace 1. Because it's a Laplace on equation 1. Okay. What about for equation 2? Like Laplace for equation 2. Well, I'm going to have E2 of S is equal to EC of S plus LSIL of S. Are we following with the Laplace transfer? Do we see why the S's go where the S's are supposed to go? Do you have any questions regarding the actual Laplacification of these equations? And yes, that is the technical term, Laplacification. Remember, when we have zero initial conditions, right? Just remember, if you're taking the Laplace transform of the derivative, right? This is S times the Laplace transform of the function. Let's actually write this in the general, right? Minus the initial condition, right? That's the definition for the first derivative, right? But in our case, because our initial conditions are 0, we just get S, right? This is why we end up with LSIL of S, right? Because there's one derivative. It's a single derivative. Okay. So now I'm going to solve equation 2 in terms of EC. All right, so turn that over, I'll get E2 of S minus LSIL of S. All right, so just solving that for EC of S. And I'm going to take this equation and I'm going to plug it in up here for EC. Right? So I'm going to take this EC, I'm going to plug it in that equation, right? So let's do that and see what happens. I'll get LS plus R, IL of S, is equal to E1 of S plus CS times E2 of S minus LSIL of S. Right, so all I did was I plugged in E2 of S minus LSIL of S for E sub C, right? That's all I did. So that whole thing has to get multiplied by C times S. And you can kind of see what's going to happen, right? We're going to end up with an S squared term, right? We're going to end up with an S squared term, which is important. We'll get to that in a second. But remember, when you see S in the Laplace domain, right, that signifies that something, you took the derivative of something, right? And so S squared would mean you've taken the second derivative of it. And that's important because we knew this was a second order system. So the overall equation for the entire system should also be second order, right? So we're going to do the algebra out and we're going to distribute our terms. Okay. We're going to do the algebra out and we're going to distribute our terms. I'll do that on the next slide. right? So I've taken that equation that I wrote on the previous slide. I've multiplied through by the CS, and I've grouped all of my IL terms on one side and left everything else on the other. Turns out that I've got my output on one side and my inputs on the other. Now, if I wanted to make the transfer function here, I could, right? And how would I do that? Well, if I wanted the transfer function of IL to E1, I would ignore E2, right? I would say E2 is 0. And if I wanted the other transfer function, I would say E1 is 0, and I would solve for my transfer function. But I don't need a transfer function here, right? I don't. All I was asked to do is find the original differential equation. So I have to inverse Laplace this. I'm going to inverse Laplace this. And you're probably saying, well, Dr. D, based on what we've done so far, I cannot inverse Laplace this because I can't match this to anything on the table. That's not entirely true, right? So let's do this out, right? We did this. Remember, we did this when we were talking about time domain transfer functions, right? I would give you a time domain transfer function and you could tell me how to get back to the original differential equation, right? And this is no different, right? Just that the S's are D's in the time domain, right? So I can multiply through here. I'll get LCS squared IL of S plus LS IL of S plus R IL of S is equal to E1 of S plus CS E2 of S. And now I can inverse Laplace this, right? Because I have some function IL of S. The inverse Laplace of IL of S, right, is IL of T, right? But it's multiplied by S squared. So I get LC IL of T double dot plus L I dot L of T plus R IL of T is equal to E1 of T plus C E dot 2 of T. And that's what, and there is the original differential equation with 0 initial condition. Right, when you get to where the red dot is, you have something of this form. Remember, S signifies the derivative, S squared would be the second, right? S third would be the third. You can just keep assigning time derivatives in this way. Right? Okay. You guys have any questions on this?
Why do we want to do this, and like why will this help, like this format and the inverse Laplace of it?
Why would you want to do this? As if you wanted to know what the differential equation was, right? If somebody gave you a random transfer function, you might want to know what the actual ODE looked like. Right? You could also solve this for EC instead of IL, right? And you would have gotten a second order equation based on EC instead of IL. We could have done that. I chose IL, didn't matter. Doesn't matter for this exercise. If you need to do something like this, you'll be told specifically what to do, right? All right, so what if I wanted the transfer function? Dr. D talked about that, right? So how do we find the transfer function? We got to go back up to that red dot equation, right? We'll do this very briefly, right? So there's two transfer functions that we can get for IL, right? We can get IL of S over E, let me use the appropriate variable, over E1 of S, and we can get IL of S over E2 of S. These are my input-output pairs for I sub L, right? Remember, the transfer function is the ratio of my output to my input. Okay. So how do we do this? Well, Dr. D said that if we look at that red dot equation and we set E2 equal to 0, right? So we'll set E2 equals 0. For those of you who can't see what I'm doing on the screen, I'm covering up that E2 term, right? So I'm just pretending that CS E2 of S is 0. It's not there, right? It is not there. And if I'm left with that, well, I'm going to divide over by E1, and I'll divide my everything else from in front of that, right? So I'll end up with 1 over LCS squared plus LS plus R. And that's my transfer function with respect to the voltage 1. Similarly, I can do things for E2, right? So if I cover up E1, I treat E1 as if it's not there, right? I end up with this. Notice the denominators are exactly the same, right? And they should be, because that's the characteristic equation for the system. What if I had solved this for E sub C? What would happen? We're not going to do it right now, because we've got other stuff to get through. But you get the same characteristic equation, because the characteristic equation is the characteristic equation, right? Some might even say that it's the characteristic equation. Okay. You guys have any questions right now? No. No question. Everybody's doing all right. Okie dokie. Important note about the transfer function, right? I said it last class, I said it at the beginning of class. I'm gonna say it again now. When you find the transfer function, leave it general. And what does that mean, right? Leave your input general. Even if I was told, right? Even if I was told at the beginning that ES is a step of 25 and ET, well, and E2, right? Even if I was told at the beginning that this is a ramp, right? Even if I was told this, I would leave it as capital E1 of S and capital E2 of S. The reason is that the transfer function doesn't care what your input is. It will work for any input, right? So it doesn't care. Leave it general. When we need to take the Laplace transform of this is when we're looking for the system response. Then we need what is E1 of S, right? right? So we can take the Laplace transform here, right? E1 of S is just 25 over S, right? Because the Laplace transform table tells me so. Plus, we derived it by hand a week or so ago, right? E2 of S is equal to 5 over S squared. Okay. You only plug these in after you multiply your transfer function by E1 of S. Then you can do your partial fractions then, right? But if you're asked for the transfer function, do not just leave it general. Leave it whatever your output is over whatever your input is. Okay? Okay. You guys have any questions? No? Okay. Nothing? Nobody? Well, let's talk about impedance, right? So that's transfer function, right? We can find the transfer function of an electrical system. It's the same process that we did for a mechanical system, right? And it would be the same process for a thermal system or a fluid, right? You get the differential equation, you take the Laplace transform with zero initial conditions, you algebra it until you get the output divided by your input, right? That's how we do it. But what is impedance, right? So resistance resists the flow of current, right? Or we could say that it impedes the flow of current. Turns out that capacitors and inductors also impede current. Specifically in an electrical system, impedance is the generalization of the ratio of the voltage transform to the current transform in the given symbol Z. So the impedance is Z, and Z is the voltage divided by the current. In the Laplace space, look, those have S's in them. This is not time domain. This is the Laplace transform, right? So given, well, all right. So this equation, does this equation look familiar at all to anybody? Does this look like something that we've seen before? What's that, Sean? Yeah, it looks like Ohm's law, right? Because it basically is Ohm's law, right? Because if I rearrange this, right, the voltage is equal to the current times the impedance, right? Which would tell me that the impedance of a resistor would just be R, right? Why does that tell me that? Well, again, let's look at this, right? We know that ER is equal to R IR. I want to take the Laplace transform of this. And then I need to make this E over, let me do it over here. So I've actually done, right? So I'll take the Laplace transform. This is ER of S is equal to R IR of S, right? So ER of S over I R of S is equal to R is equal to Z of R. Right? Because it is. It is. Okay. Yeah, Sean. So when we talk about, we'll see how this works in a minute, right? So the transform, the impedance transform of R is just R. That's what it ends up being. We'll see that it differs when we have capacitors and inductors and stuff. Okay. So far, everybody's with me, right? So we're going to do the same thing. We're going to do the same thing. I'm going to erase this down here because I didn't give myself enough room, right? Typical. All right, so what do I know, right? I know that I sub C is equal to C E dot C, right? I'm going to take the Laplace transform of this. I'm going to create my voltage divided by, so I want EC of S over IC of S. That's going to be equal to ZC of S, which is equal to 1 over CS. So the impedance, right? So essentially, what are we doing? We are taking these things in the time domain and we're normalizing them by basically using Ohm's law, right? And so we say that the impedance, the amount of current being impeded in this system is 1 over CS, right? So we can have that. We can do this one more time with the inductance, right? Because we know E sub L is equal to L I dot L. So you guys work on that, the E sub L one, right? And somebody report out to me, what is the impedance Z sub L? Remember, I'll give you this one. In case you don't remember or you don't have your master sheet. Get me the impedance. Get me the impedance. Where we go? What do we got? What's the impedance? Does anybody want to volunteer? I'm gonna have to do the thing where I'm gonna poke my screen with my one. I got a 1 over L. Do we have anybody else have any? Do we agree with that? What's going on? Let's get an answer for somebody at home. Someone at home.
Wait, can you repeat what he said? Because I didn't hear it at all.
Over LS.
I got that, but I don't know if that's right. I just was being dumb.
Okay. All right. So we've got two independent responses. But you guys are inverted. So we take the Laplace transform of EL is equal to L I dot L. We get EL of S is equal to LS times IL of S. I want to create EL over IL. So all I have to do is divide out my IL, and I'm left with LS. So the impedance of an inductor is just these now, if we're going to be doing the impedance method, these now become part of our truths, right? We don't need EL is equal to L I dot L. We don't need, EC is equal to, well, I won't say we don't need them, okay? But we're going to be dealing with this because there's some very specific stuff that this allows us to do. The S is the dot, right? So yeah, you already took it into account when you made it LS, right? Okay. So here we are, right? We've got R 1 over CS and LS, right? That's what we've got. How is this useful, right? Because we're not seeing it, and I appreciate that. But turns out that because of the way that this is defined, we can start to do things like collapse two branches of a circuit that don't have, right? So we can make an equivalent impedance, right? So if I had like a capacitor in parallel with an inductor, I can make an equivalent impedance and collapse those instead of having to leave them separate. Right? Impedance is useful because we can combine individual impedances with series and parallel laws to find the impedance at any point in the system. And they follow the rules for resistances, right? Because essentially we've used Ohm's law to create this, right? We've normalized everything based on the amount of impedance, the amount of resistance that we have from each of these elements. So impedance in series, we just add up our impedances, and when they're in parallel, we take the reciprocal rule, right? So 1 over the sum of 1 over my impedance. When can we use them? In series. In series, we can use them when the impedances have the same current going through them. And in parallel, we can use them when you have the same voltage drop going across them. So, and this is where the power of impedance happens, right? Because we know that doing this in the time domain gets really ugly really fast, right? Anytime you add a capacitor and inductor, you're adding an order to your system, right? And so doing loop analysis becomes arduous and really, really tedious and a pain, right? But doing impedance allows us to take a lot of those extraneous loops, collapse them down, and come out with a differential equation, right? Through the power of Laplace transforms. So, this is one of those things, right, where, and I've said this a couple of times, right? If you're told to use a specific method, use that method, right? If you're not told to use a specific method, do it however you like, right? But if you're specifically asked to do something using the impedance method, we're going to have to do that. And what does that look like? Well, that's going to look like this, right? So here's a circuit, right? And specifically, I'm asked to find the transfer function of my output voltage to my supply voltage, right? Well, this is different than what we normally do, Dr. D. You told us that we should always use EC and IL. I did say that, but there are exceptions, right? Like when you're specifically asked to find something. And with impedance, it's actually not so bad, right? Because if we didn't use impedance, right, we'd have to, say, well, this is a node and that's a node, and I've got to figure. I know that the voltage drop here is the same as this one, and you have to come up with creative ways for figuring out what all these things are, right? But with impedance, it's a little bit cleaner, right? So let's draw our circuit. All right, so we'll call this one here I sub C. This one on the top branch is IR2. We've got I1 coming in, right? We were told that that's, I'm just gonna mark these as A and B. We're not gonna need them though. Right, and this was E sub S, and this was E out between here and here. Right, remember, the terminals are just telling us that we've got, that's what we're measuring, right? Imagine you got alligator clips and you're going into your circuit across that resistor, and I'm gonna grab that voltage. Okay, so I want the voltage V naught to V supply. Okay, V out to V supply. Okay. All right. So we're gonna use impedance, right? We're gonna use impedance because we were told, right? Remember, use the impedance method. Okay, well, first thing that we can do is we can make an equivalent impedance for this. They're in parallel. They both have the same voltage drop. We can make an equivalent impedance, right? So we'll call this ZEQ1, okay? So, right, I'm gonna leave that there. We can't forget to do our other steps though, right? Inputs and outputs. I've written these as capital, so I mean, I've just put them in the Laplace domain. It doesn't really matter one way or the other. They should be the same. What about my truths? Well, my truths here tell me that I know ZR of S is equal to R. ZC of S is equal to 1 over C times S. And I also know that the voltage drop across E out is equal to R1 times I, we'll just call it I of S, some current coming out there, right? There's some current coming out here, we'll call it I. There's just some current. All right, so we're gonna take this block here, we're gonna collapse it down into a single impedance that talks about both. Okay. So how do we do this, right? I'll do my reduction. Well, they're in parallel, so 1 over Z EQ is equal to R, or 1 over R, sorry, let me do that again, 1 over R, plus 1 over CS. Right, 1 over ZR plus 1 over ZC. That's what it is. I can algebra this a little bit. And this should be R2. Excuse me. Right. So this is going to be 1 over R2 plus CS, right? Because 1 over CS is just, flips up to the top. Sorry. This is plus 1. All right. So common denominator multiplied CS by R2 over R2, right? So I get R2 CS plus 1 over R2. Yeah. Everybody cool with that? Let's take a step here. 1 over R2 plus R2 CS over R2. All right, all I did was multiply it by 1, so it doesn't change anything. Common denominator. Why do I want to do that? All right? Because this is equal to 1 over ZEQ. And I need ZEQ. So I have to take the inverse of this, right? So ZEQ1 is equal to R2 over R2CS plus, which looks a little bit more like something that we've seen. I want you to look at this denominator here because that's the standard form for a first order system, right? And we should expect that to look like that because that's just an RC circuit, and that's what we should get from it. If that's in standard form already, which Dr. D claims that it is, what's the time constant? What's first order standard form look like? What we got? Any takers? Wild guesses are welcome. What's that? Yeah. So what's the time constant there? So from the master sheet, Melanie pulled tau y dot plus y is equal to something, right? So what is tau in this case? What's tau? R2 times C. R2 times C is my time constant. Okay. So that's Z1 EQ, right? Z1 EQ. So what can I do now, right? Well, I'm going to redraw my circuit really quick. So here's ES. Well, you know what? Since we have impedances on the board, let's make this E sub S of S, right? And I've got this impedance, and I'm going to draw my impedance, and it's going to look just like a resistor, which is not confusing at all, so don't worry about it. Right? So this is my new circuit after I've made my equivalent impedance. There's some current now that I'm going to call I of S coming through here. And notice it's not a node anymore, right? That's a terminal, so that doesn't count as a node, right? So this is now a single loop circuit. So now all of these things have the same current that go through them, right? And what was the rule for adding impedances in series, right? Well, they needed to have the same current going through them. So we could reduce this one more time, right? We could reduce this one more time. But we're actually not going to yet. Right? So let's talk about this, right? So I have this equivalent impedance, right? Remember, that's going to be equal to ES sub S, right? Divided by well, no, not yet. Please hold. I got ahead of myself in the notes. Please hold. I apologize. So exciting. Okay. So we know what E out is, right? We know E out is going to be I wrote it down somewhere as R1 times IS, right? That's we know that. So that's going to be helpful later, right? But what we need to do now is we're going to take these two and we're going to combine those, right? Because what do we want, right? We want a direct path of, E out divided by E sub S, right? We want the output voltage to the input voltage, right? That's what we want. So how do we get that? Well, we can combine this into one more element and then it's just going to be a straight shot, right? Because you get all E out is the entire voltage drop, right? So if I want to call this ZEQ2, right? Well, these are in series, right? So this is just going to be ZEQ1 plus ZR2, right? So this is, oh, sorry, ZR1. I don't know why they labeled them 1 and 2 where they did, but that's fine. So this is what? Well, this is R2 over R2 CS plus 1 plus R1. And this, and we will algebra this a little. Okay. So same common denominator trick, right, that we did last one. Multiply R1 times R2 CS plus 1 over R2 CS plus 1 to get the same denominator, which leaves us with that mess right there, right? And as written, this entire thing is equal to what? Well, this is equal to, wait for it, this is the input, right? Because this is an impedance, that's my input voltage divided by my current, right? Not exactly what we want, but it's close, right? It's close. It's got that ES part. Got that ES part. So how are we going to get this? Well, we need some way of relating that current back to the output voltage. Only we had a way of doing that, right? Only we had a way of doing that. If only. Because we know that E out is equal to R1 IS, we can say that IS is equal to R1 or E out over R1. So let's write down, I hope I have one more slide here. I do. Perfect. So let's write down what I have here, right? So we know that E out is equal to R1 I of S, which tells us that I of S is equal to E out over R1. I know that E S of S over I of S was equal to R1 plus R1 R2 CS plus R2 over R1 R2 CS plus 1. Oh, okay. We're gonna put that in there. All right, so we'll end up with ES of S over E out over R1. Now here's where it gets This is going to be the funky algebra. Right? Well, it's not funky algebra, right? So, all right, E of S over E out over R1, right? This is just me, the same as me writing this, right? Right? Well, it's just the same thing. Yeah. Or if you don't like doing that, what if I change this to be multiplied by I of S, right? I just bring the I of S over, right? And then I would multiply this whole thing by E out over R1, right? We could do that. That's fine. Okay, so if I do that, right? I do this, I can bring this back over, right? So this is, depending on how you want to do this, this is kind of an extraneous step. Because what we really want is E out to ES, right? But I'm constructing the inverse of that right now, right? I don't have to, right? But for the sake of multiplying through, we're going to. And if I multiply through on the base by R1 here, right? I get that. Right? No, I'm good. I'm good. So I just flip it. Did I algebra wrong? Oh yeah, I see it. I see it. That should be there. Yeah, yeah, yeah. Sorry, I put an extra R1 in there. My bad. R1 squared R2 CS plus R1 R2. Right?
Wait, why did we bring the E naught of S back? Like
Because
to be
Carl,
over.
because I did it the long way, Carl. That's why. You could have left E out over there, and you could have divided by E sub S, and then brought the other thing, flipped your fraction and brought it over to the other side, right? Could have done that too. But I just am doing it the long way. Because what I really need, right, as instructed by the problem, sorry, I almost wrote that the wrong way, is E out of S over E S of S, right? That's what I need. So, good question. That shouldn't be there either. You know what happened? I apologize. I looked at the numerator. Well, instead of looking at my notes, I looked at the numerator and multiplied through by R1. Good catch. My bad. Sean, what's up? You mean this one right here? This one? This one right here? Did I accidentally put an extra R1 in? Potentially. Yeah, looks like I did. Ah, okay. So this one's not supposed to be here either. That makes so much more sense now. There's only one R1 in the bottom. Okay, Sean caught it. I apologize. If you go back up to that equation at the very top, right there, the E of S over I of S equation, There should be no R1 in that denominator. I'm batting 1,000 with these right now. Right? This is Hall of Fame numbers. Okay. So now that we have it in the appropriate algebra, E out of S over E S of S is equal to R1, R2, CS plus R1 over R1 plus R1, R2, CS plus R2. There it is. That is the transfer function. That is it. Notice it's first order. Right? It's first order, which should hopefully make sense because we only have one capacitor in this entire system, right? If we wanted the differential equation for this of E out to ES, right? We would cross multiply and then take the inverse Laplace of these terms. Okay. So, super good, right? Easy case. I think we have time for a bonus one. They didn't even put on the guidance sheets. Why don't we do that? We'll do one more. Let's see if I have an extra slide. I'll put in a note. Excuse me. Oh, of course, good. You guys have any questions aside from my shoddy algebra? Where it's all right in my notes. Stop trying to do it down for my notes. Aside from Dr. D's shoddy algebra, we deal with the process of how to do this, right? Take the things, you collapse the things, right? If you have things in parallel that have the same voltage drop, collapse them. If you have things that are in series that have the same current going through them, collapse them. What you're going to notice is, just like we did in this problem, you have to start by getting things into that form, right? So I started with that block on the top because I can't combine the impedance of these other blocks, right? Because they don't have the same current going through them in series. I had to start with the parallel so that I could get everything in series with the same current so that I could combine that again, okay?
I know we didn't actually use any Laplace, but I'm just a bit confused on why what is the S? Like, is it, because I assume it's not, is it the same one when we
It's the
use
Laplace
Laplace
variable,
transform?
Carl. Carl, all of this is in Laplace. We didn't explicitly do the Laplace transform of anything,
We just were,
but
oh,
because we're using impedance, you're automatically in the Laplace domain.
oh, okay.
Impedance,
Yeah,
the way
that
that
makes
we got
sense.
our impedance factors, right, or impedance variables, was by taking the Laplace transform of our first order ODEs, right, our element equations. That's how we got it. And so essentially, right, we've already done it. It's a very sneaky Laplace. Okay. Do one more impedance problem for a circuit. You guys have any other questions?
Dr. D, I have one question.
Yes.
Where did, in like the equation, where did the R1, R2, CS come from in the numerator?
This one right here.
Yeah.
Go back. So we just made the common denominator for this, right? So if you multiply this by R2CS plus 1 over R2CS plus 1, you'll end up with R1 R2CS plus R1, which is the second part, right?
Okay, thank you.
That's all. Any other questions? All right, so I want you guys to look, as the kids say, I want you guys to peep this diagram, all right? Just peep this diagram. I said it. Can't take that back. I wish I could. Kids don't say that. Oh man, I might be out of touch. Shocking, I know. All right, here's a diagram. Yes, that is a current input. I want you to find E out of S over I of S. I'm gonna give you guys until 11:45 to run through. You should use impedance. Use the impedance. Is that an assumption, Sean, or do you know that because they're in parallel and they have the same ground? So yes. Mm-hmm. All right, 4 more minutes. Guys at home have any questions?
I guess my question would be, think I've understanding it before. At one of our truths for the previous problem, when we figured out what is E naught or E zero, and you said it based on equals like R1 times some sort of current. I guess my question is, would it just be the same, but except it's the capacitor times some sort of current, or are we looking at it differently now because it's a current that's coming in originally?
So, good question, Carl. Compare what we were asked to find in the last problem versus what we're asked to find in this one. Okay. And then you'll see why we needed a way to map the two. Any other questions? Couple more minutes. All right, 11:45. What's up? What's going on? Why don't we do this? What's my input? What's my output? Somebody tell me my input, somebody tell me my output. Do it piecewise. All right, Sean, a little bit louder. Exactly. The current, right? That's a current source. We've got I of S in and E out and S out, right? What about my truths? What should I write down for my truths here? This is an impedance method problem, right? So what should I be looking to do here?
For truths would be your impedance, so it'd be the R, and then for the resistor, and then for the it would be LS, and then 1/CS for your truths on the impedance.
Exactly. Yeah, you could do that if you wanted to, right? But so that's what I was trying to get at with Carl. Right? Carl's question was from earlier: do we need to make E not equivalent to anything, right? Because we did it in the last one. And the reason we had to do it in the last problem is because we were being asked to find E sub out over E sub supply. right? We're asked to find the output voltage over the input voltage. In this case, we are asked to find the voltage divided by the current, which is just equal to the total impedance, right? So if we can get ZEQ, we just have the answer here, right? Because ZEQ is equal to E out over I sub S. So we don't need a way of math. Now, if this asked you, like, if this was a current, this was a voltage source instead, right? And you needed to map those things together. Well, you know that E out is the same as EC, right? Is the same as EL, is the same as ER, right? So you could potentially write that in terms of any of those other things, right? Any of those other currents. Well, we don't have that, right? So all we have to do here is collapse all these things into one equivalent impedance, and we're done. So how do we do that, right? Well, they're all in parallel, right? They're all in parallel. So they're all in parallel. So can't we just use our reciprocal rule to add them? And the answer is yeah, exactly what we're going to do, right? So what I'll do, right? 1 over ZEQ is equal to 1 over R plus 1 over LS plus CS, right? Because 1 over CS is just together. Right, continuing on, I make my common denominator here, right? My common denominator is going to be RLS, right? Because I need to add up 1 over R plus 1 over LS, which gives me RLS. And the other one doesn't have a denominator, so that's just going to be RS or RLS as well, right? So I get LS over RLS plus R over RLS plus RLCS squared over RLS. Okay. Yeah. What's up?
Sorry. For so like the second line, how did you get your CS to become squared if you're just trying to get RLS on the bottom? Is it because you,
RLS over RLS times CS.
oh, wait, no, oh, the S.
Yeah. Right. Because
Okay.
remember, to get the common denominator, you have to multiply by 1, right? And
Yeah,
so,
sorry, I was, yeah.
no problem.
I was thinking that the like CS was together, not like C and then S.
Yes, gotcha.
Thank you.
Yeah, it's not C sub S, it's C times S.
Dr. G,
Yeah.
someone in Discord just asked for you to let them into the class.
Got it. I suppose. I guess. Okay. So then we algebra, right? So we've got RLCS squared plus LS plus R. That looks an awful lot like a second order characteristic equation. Have I've ever seen one divided by RLS. But that's 1 over ZEQ, so I have to flip it. Right, so ZEQ is equal to RLS over RLCS squared plus LS plus R is equal to E out over I of S, which is exactly what we're looking for. We're done. Problem done. We can redraw our circuit. Looks like this. And no big. So, I think we can fit one more. Do one more.
And just to confirm, it was just E0. It wasn't like E0 of S.
It is of
But
S.
it's the same thing.
Technically, it's all of S, right? I just didn't write it. If you see a capital letter, it's going to be a function of S unless it's a current, because writing lowercase I dot is annoying. So I just don't do it. I use capital I. Right? Because then you're like, why is there a semicolon over that weird looking L? It's not worth it. My handwriting's bad enough as is. Just wait until we start having things that like say 5S. No one's gonna know. And, okay. So any other questions? All right, so impedance makes circuit problems a lot easier, right? Because if we can combine these things, right, we've simplified what we have to do. And look what happens. We automatically get a second order differential equation out of this, right? That RLCS squared is my characteristic equation. It's already second order, right? I don't have to worry about combining the parts after the fact. I don't have to get two equations, right? I just have to make sure that the order of the system is met, right? But the big question, right, that I know you're all asking, you're all clamoring for, is can you apply this to op-amps, right? And the answer is yes. You can totally apply this to op-amps, right? So if I wanted the transfer function of my output voltage to my input voltage for the op-amp shown here, could I do it? And sure, and I can do it using impedance. All right, so we know, right, our input is IE of EI of S, our output is E out of S, right? Now this is drawn a little bit differently than how we normally have been looking at them. So let me redraw it. So this has right. That kind of looks like what we would do. So I've got my drawing of it. So how are we going to handle this, right? Because that R1C on the top branch is nasty, right? Well, we can make an equivalent impedance with that, right? So let's fill this out, right? Let's get our truths going, right? Remember, for op amps, we've got EB minus EA is equal to 0, right? So the difference in my terminal, but we know that EB is also equal to 0. Therefore, EA is equal to 0, right? Because EB is at ground. Excellent. I know that IA is approximately 0, right? We're pulling approximately 0 current here. Right? And from the KCL at A, I know that IR1 has to be equal to, let's call that IC, right? Or did I call that IA? It looks like I might have called it IA here. That's unfortunate. Let's go there. That's not IA. That's IC. This is IA, right? Going into A. Right, so it's IC. It's equal to the current through that top branch, which is IC. Okay. All right, we need our impedance. So I can make an equivalent impedance, right, for that top branch. And so we'll do that, right? We'll say Z EQ, well, that's in series. This is just going to be 1 over CS plus R. I believe we called that one R2. Just leave this general. Which gives me this. So we gotta come back here, right? What is the voltage drop across that first resistor? This is just E in of S minus E A of S. Well, the Laplace transform of 0 is still 0, right? And that's got to equal R1 times I R of S, right? So let's rewrite this, knowing that this term is 0. I get EI of S over IR of S is equal to R. Huh? Yeah. Okay. That looks like impedance, right? That makes sense. We'll call it R1 since it's R1. Well, I know ZEQ, right? ZEQ is equal to this voltage drop E out because everything across there has to drop by E out. Right, but really, right, let's talk about what it really is. It's really EA minus E out, right, which is still 0, divided by IA. Sorry, IC of S, right? Okay. So I know that IR is equal to IC, right? I know that. That's something that I wrote from my KCL. So can't I solve one of these for IR? Sure. I'm going to solve this one for IR. And I'm going to plug it in to IC down here because IC is equal to IR, right? This whole problem, just like when we do it in the time domain, this whole problem hinges on this KCL, right? KCL still plays. So I'll get ZEQ is equal to negative E out over R1, right? R1 over E. Let's make sure. I did that the wrong way. Sorry. Dr. G's algebra mistakes continue today. This should be E in over R1, right? Because multiplied by that, bring that R1 down. Geez, on a roll, right? So we've got negative E out divided by E in. These are all of S, right? Divided by R1. And this is equal to negative, oh, I'm sorry, not negative. This is equal to R2. R2 CS plus 1 over CS. Everybody cool so far? We good, aside from my giant algebra mistake at the beginning where we're good. Because now look, we already have E out over E in, which is what we need, right? We just need to multiply both sides by -1 to get rid of the negative. And we need to divide by 1 over R, which is the same as dividing by 1 over R. Okay. So we end up with, sorry, not ZEQ. We end up with E out of S over E in of S is equal to negative R2CS plus 1 over R1 CS. That's the transfer function. That's what we asked to find, and we're good. Right, and so, right, simplifies some really nasty looking offense sometimes. We don't have anything else planned for the rest of the class because we have a bunch of problems that I know you guys got yesterday, so you probably haven't had a chance to look at them. So look at them, try them before next class, and that's what we're going to pick up with the problems on the sheet, right? Those are going to be a little bit lengthier because you're being asked to do things from the beginning all the way through the end. Right? So you have to make models for most of them, and you're going to have to do either Laplace transform, impedance, or wait for it, transfer function method, and it'll be very clear what you need. Okay. Good. Okay. That being said, do you guys have any questions on this? Don't go yet because there's one thing regarding participation that we need to talk about before we go. All right. Does anybody have any questions on this? Right. So what's the takeaway here for impedance? Right. Use it for circuits when you can. Right. Personally, I find it to be. It helps simplify things greatly. Right? Condense things where you can, but be aware of what you're being asked for, right? Be aware of what you're being asked for. You're either going to be asked for a transfer function or you're going to be asked for the impedance directly, one or the other, right? So just keep that in mind. Keep that in mind when you're doing it. Okay. Impedance is not covered in the textbook, right? But there is a document on LoudCloud in the path that is an extra resource regarding impedance. So please take a look, ask any questions. Note on office hours for tomorrow, I have to unfortunately cancel them. I got pulled into another meeting Wednesday afternoon, but the rest of the week they are as usual. So today from 3 to 5, and Friday from 3 to 5. Okay, participation will be due by Thursday at 11:59:59. So I have decided that I deserve my own signature meme, and that you guys are going to provide one. So in your teams, create a signature meme, right? I'll post on LoudCloud where you can upload it. It'll probably be just, just private forum it, okay? One submission per team, PG-13 tops, okay? Sean. Yes. Just at least tell me who your group. Well, I guess you don't. I know what the teams are. So just put your team name, right? Just to remind me, and everybody will get credit as long as one person submits it by midnight on Thursday. Because on Friday, Dr. Staggs, Dr. Wright, Professor Tomford, and Professor Price are going to judge your memes, and the winner from each class will get 5 trackers. Straight up. Okay. And then also they will be showcased at various times. That's obviously, that's the point of it. Okay. Next class, we'll do more problems. We will start off by going over the exam stuff. By that I mean like how to like sign into it, because we're going to be using test mods instead of LoudCloud this time, right? So I'm going to go over the instructions on how to do that. We'll go over all that stuff. So bring your questions about like exam format and logistics, right? Also bring any other questions too. That's fine. But try those problems, right? Try those problems. Some of you got assigned problems. It was done totally at random. So remember, if you were assigned the problem, you're going to have to lead the discussion on it, right? So just remember that. Okay. Cool. All right, that's it. We're going a little bit early.